Hello again. Welcome back to our GPU optimization of Advanced Encryption Standard course. So in the first lecture, we talk about block ciphers. Now in the second lecture, we will see Advanced Encryption Standard. So before moving on to Advanced Encryption Standard, let's see how the history actually occurred in this area. So in the past, the most famous encryption algorithm was Data Encryption Standard, DES. So it was designed by IBM in the 1970s. It was based on an earlier design by Feistel. So unlike AES, this was a Feistel design. So in 1976, NSA tweaked the algorithm by changing its S boxes, also shortened the key. So its block size is 64 bits. The key length is 56 bits, which is really short, and it consists of 16 rounds. Currently, it is known as Data Encryption Algorithm, DEA, not standard, because it is no longer standard, and it wasn't a standard for a very long time, but people kept using it. This is why we even changed the name, because it became useless after 1990s, since its short key is susceptible to brute force attacks. So actually, crypto community stopped using it during 1990s, but in real world, people kept using it, which actually caused a security problem. So why I call it there's a short key? This is because an attacker that captures a single ciphertext ciphertext block, for instance, can try to decrypt it with every possible key to check if it provides a meaningful plaintext. Such an attack is called exhaustive search or brute force attack. So exhaustive search is a generic attack. This means that it is valid for every cipher. So we actually here not finding any weakness in the design. We are simply focusing at the key length. So for a k-bit keyed cipher, the attacker is required to perform at most 2 to the k encryptions or decryptions. Thus, security of a block cipher is upper bounded by exhaustive search. So let me show you how hard it is to perform a brute force attack. So this, as I mentioned, has a 56-bit key. So this means that there are this many possibilities for a secret key. But if you increase your key length to 80 bits, which are currently there are many standards that uses 80-bit secret keys. So it's the key space increases to this number. But if you use AES, the shortest key length you can use is 128 bits. And as you can see, the key space increases exponentially. So if you want military grade security, you should choose your secret key as 256 bit. So in order to understand how large this number is, so the number of atoms in the observable universe is also around this number. So it is super large. So increasing your secret key length slightly increases everything exponentially. So the attack becomes super hard. So this is why actually AES supports 128-bit key for personal use. It also supports 192-bit key, but it also supports 256-bit key, which generally we refer to as military-grade security. So Advanced Encryption Standard was actually named Rheindahl. It was designed by John Damon and Vincent Raymond, two Belgian cryptographers, and the name of the algorithm comes from the letters from the names of their designers. So NIST had a competition in the late 1990s because this was broken. And the competition name was Advanced Encryption Standard. And since Rheindahl won the competition, it is now known as Advanced Encryption Standard, AES. So the block size is 128 bits. As I mentioned, it supports 3 key lengths. And the number of rounds actually depends on the length of your secret key. If you are using 128-bit secret key, the number of rounds is 10. But if you use military-grade security as 256-bit key, the number of rounds increases to 14. Sometimes this is counterintuitive for the students because they think that if I increase the key length, the algorithm becomes stronger. So they expect to have less rounds. But actually, if you look at in the information theoretical sense, you are combining a plain text block with the secret key to hide this information. than obtain the ciphertext. So if your key length increases, the amount of data you are trying to hide actually also increases. So this is why you need more rounds to provide more diffusion and confusion. So it is a substitution permutation network type block cipher. There are many attacks for AES, and cryptographers try to analyze it since its introduction in the late 1990s. So all of the known attacks are ineffective. So currently it is secure to use AES, and almost the whole world uses this algorithm. So let's see how the algorithm works. As we mentioned, a block cipher first divides the plaintext into blocks. So we are focusing on a single block in this lecture, and in the following one, we will focus on how to encrypt larger data. So the 128-bit plaintext input is actually represented as 16 bytes, and those 16 bytes are represented as a 4x4 matrix. Okay, so your 128-bit plaintext block actually divided into bytes and put inside this box. A byte can be treated in two ways when dealing with AES. Either you can see it as a string of 8 bits, which is the easier way to look at it and do the implementation. But some operations are done in the Galois field. So you can also see a byte as an element of the Galois field GF2 to the power 8. So arithmetic in Galois field is a little bit more complicated than normal arithmetic with numbers. So AES uses the Galois field defined by the following irreducible polynomial. So a byte can be represented by a degree 7 polynomial where the bits of the byte corresponds to the coefficients of this polynomial. Now we can perform addition and multiplication on these polynomials modulo RP. This more mathematical representation is better to understand the security of the cipher. But anyway, we won't be needing this approach. We should know that some operations are done in the Galois field. So let's focus on AES now. One round of AES consists of 4 operations. Key addition, shortened as AK. This is just the XOR of the 128-bit round key with the 128-bit input. So if you don't know what the XOR operation is, it is exclusive OR. So it is just addition modulo 2. So you are simply adding bits. So here you have 128 bits, but you are doing it in modulo 2, so there are no carry bits. So it is just like a regular addition without any carry bits. The second layer consists of sub-bytes, shortened as SB. This applies 8x8 SBUCs on all of the 16 bytes. So this part actually provides confusion. XBUCs is just a table where you have you can see which input provides which output. So it is just a table lookup operation. Shift rows, SR, rotate rows to the left. So you provide diffusion at the level of rows. So in order to also have the diffusion at the columns, we have the final operation which also provides diffusion, but for the columns, you multiply each column with a matrix M. Okay, so the general picture is like this. So you have your input, 128-bit input, but here represented as 16 bytes. All of the boxes represent a single byte. So at the key addition layer, you simply XOR your 128-bit round key with the 128-bit input. You write the result back. Then you take each byte and send it to the SBUCs, which is just a table lookup operation, and write the result back to its place. So you repeat this operation 16 times. Then we have the shift row operation. So top row actually rotated 0 bytes to the left, which means that it stays the same. You can just see at the positions of X to see it. So the first row is rotated 1 byte to the left. So this is why this X actually comes here. So the second row rotated 2 bytes to the left. So X comes here, and the third row rotated 3 bytes to the left. So for instance, this one comes here. So finally, we take each column, multiply it with the matrix M, and write the result back to the position of the same column. So we have 4 columns. We repeat this operation 4 times. So this is just one round. So you repeat it 10 times. for AES 128-bit version, but if you have larger keys, you repeat it 12 or 14 times. So let's look at the SBox operation. So this is the SBox of AES, which is carefully chosen. It provides good resistance against differential and linear cryptanalysis. And you can use this table as follows. So if your input, for instance, is 3B in hexadecimal notation, you simply take the first nibble of this byte, 3, so you look at the row 3. And here the second part is B, you look at the column B, so you end up with the value E2. So for the input 3B, the output is E2. This is how you provide actual confusion. And you repeat this process for every bytes for that layer. And the mixed column operation is just a matrix multiplication, and this is the matrix of AES, which is again carefully chosen, and it is a matrix coming from coding theory, and it provides good diffusion. So what you do is as follows. So this is your column. You multiply this matrix with this column and write it back. So if you don't recall what a matrix multiplication works, so you take this value 2, multiply it with x0. You multiply 3 with x1, 1 with x2, 1 with x3, and XOR all of these values and write the result to y0. Then take this row, also multiply this row with this column, write it to y2. Take the second row, multiply with the column values and write it to XOR the results and write it to y2, etc. The important thing is that this matrix multiplication is omitted in the last round. This is important. So when you implement AES, the last round behaves differently. So you cannot write a for loop for 10 because the last round doesn't have this matrix multiplication, because actually it's just to provide simplicity and to simplify the cipher, but this also causes some problems because in all of our implementations we have to treat the last round differently. So the only thing we haven't mentioned is the key schedule. So this is the key schedule for the 128-bit version. So the 128-bit secret key is actually your first round key. So if we go back to picture, here we XOR the input with our first round key, and this is our master key. But in the next round, we will use another round key, and that round key is actually calculated from this key schedule algorithm. So you write your 128-bit master key again as a 4x4 matrix, but actually we can also treat it as 4 columns, 32-bit values. And the rightmost column treated as follows. You rotate it 1 byte to the left, then perform SBox operation on, 1 byte to the right, actually, your left, sorry. Then apply the SBox operation on all of these 4 bytes. Then XOR, also there's a round constant addition, which is not shown in this picture, but you add a single byte value, XOR a single byte value to one of these bytes. Then XOR with the leftmost column, and you write it back. And also XOR it to this 32-bit value, write it here, and so on. So the top one was our master key. Now this is our next round key. In the following round, we take this to the top, perform these operations again, and obtain the next round key. So since the round keys can be calculated only once for the whole encryption, it doesn't matter if you're encrypting a 1 megabyte or 1 terabyte file, you can do this operation only once and store the round keys and then use them. So this operation doesn't need to be optimized much in practice. Of course, if you are using the encryption algorithm for encryption, but not for some other purposes. So this concludes our discussion of Advanced Encryption Standard. So in the next lecture, we are going to talk about mode of operations. Because when we use a block cipher, we need to choose a mode of operation to determine how we encrypt plain text that is larger than a single block. So until so far, we only focused on a single block, but then we have to focus on large files or large input. So some mode of operations are not secure. We will show some examples. And some mode of operations allow parallelization and some of them does not. But since we are going to do a CUDA implementation, we want to have parallelization, so we will see a mode of operation which is suitable for CUDA optimization. Thank you for your attention.